questions can be derived off of this slide. Okay? So, lift to drag ratio, airfoil efficiency, that's a good thing to know. L/D max, most efficient AOA, does a lot of different things. However, as we'll see later, there's differences between min drag point on the thrust required versus the power required curve that I'll highlight later. But jet aircraft have different performance things at L/D max or min drag than do other aircraft. So we need to make distinction between those two. Aspect ratio, remember the two things. So the simple thing, span chord, or the more difficult one, span squared over area. That would go, so, and again, you're not going to be doing mathematics on this, but a multiple guess question would be derived there. Okay. You can see it.
I wrote another note.
We've always talked about the four forces. We go lift and compensates for weight, right? Thrust for drag. And we seem to think those as equal things, but really it's not entirely like that. Because when this is the part of the drag force, we've got relative wind is deflected, and as a result of that, the reason that deflection is we've got lift production, and so we've got two components. We've got lift and we've got induced drag. There's components that make up that. So, ground effect. The function of ground effect, wingspan, height above the ground, and does it matter whether it's high or low mounted? Yeah, it does.
Yeah, it does. Float a lot more.
Because it's all based on where the wing is in relationship to the ground. Okay, so low wing is going to come into ground effect earlier than, or actually, yeah, at a little bit higher altitude than a high wing airplane. These are nice things to know, but I don't think I'm testing you on that. So primarily that right there. All right, the equivalent parasite area, what would this also be determined? What we also call it, if we take induced drag out, and we've got just parasite drag, what do we call that when we compare airplanes? Flat plate. Okay? And so the way we do that is we take, wind tunnel, zero lift, so AOA, even if that's a negative AOA, until it's producing zero lift, and whatever drag is resultant is all parasite, we get flat plate area as a result of that. Parasite drag varies with the square of velocity. That's important. Not the formula, but just that fact. Okay? Just that fact.
Parasite drag varies.
Square of velocity. Next time, do I need to put highlighters around this thing? Is to highlight exactly? No, we're not doing that. Yeah, there's more good stuff on it.
Let's go over that.
Okay. Force and what makes up that? And what does this look like? This looks like, that looks like the equation used for jet engines. Oh. So remember what Q is?
The inlet area.
It's mass air.
Mass air.
Okay, so it's density and all that stuff is included in that. So you get mass air times the exit velocity minus the inlet velocity. So the difference between the velocities of air and the whatever is made up with the air density, and that's what is thrust. Okay. We would like to have specific fuel consumption. Low numbers would be good. And where those low number occurs for turbojet aircraft, one of them is counterintuitive. High RPM is the most efficient fuel use. Doesn't mean it burns less fuel, but it's the most efficient.
And again, M is military flight.
Yeah, no power.
No afterburner, right?
Yeah, no afterburner. Okay, and don't worry about that. This chart, don't worry about the chart so much. It's the function of turbojets. When are they more fuel efficient? Low altitude or high altitude?
Low altitude.
What? When do they burn more fuel? High altitude or low altitude?
What do they burn more?
They burn more fuel at low altitude. So the higher they go, the better. There's a limit to that, though. When does that stop? Troposphere. So when the temperature basically stays the same from that point on, now you get decreased air density, but no decreased air temperature. So it doesn't help. So all the way up, it's more efficient, effectively, the higher they go, but also at high RPM. And that's the counterintuitive part. So you get the best specific fuel consumption, the most efficient use of your fuel at high RPM as opposed to low RPM in a jet engine, which is like, so high RPM, high altitude to a point, okay? Yeah, so that's the other part of that. Fuel flow inversely proportional to altitude. So the higher you go up to the troposphere, then it changes. So see, at this point right here, roughly 35,000 feet, you start losing that advantage because the temperature remains a constant at that point. Okay. Good. So we've got thrust available and thrust required, and we already did the problem over here, like rate of climb, rate of sink. So where I could go, what kind of curve would this be? If nothing else,
I can't see.
oh, sorry, it says thrust here,
It's jet.
so it's jet. Okay. Plus, you can tell this type of curve is not going to be quite the same for that. Thrust available, and if I gave you a thrust available, you could look and see this thrust required, notice it's the same as drag. So, again, so this is total drag and also thrust required for a jet aircraft, so those are both the same. I could tell you if I have X amount of thrust available, where would be the point where I could, and let's say at given airspeed, again, like we did here, what is my thrust, excess thrust available? That would be simple, like where I am here, this is the thrust required. What have I got available? Subtract the two, that's the answer. Boom, simple as that, right? So what is my excess thrust? So that'd be very simple to do. Okay. This is important. Okay. Bottom of the curve min drag for a jet is L over D max. Not so for the propeller-driven airplane. We'll see later. But remember that these things happen at L over D max. Okay. Range, maximum climb angle, max endurance, those all occur at that point for jet aircraft. Let's see. And I don't have this on a slide here, but if I was to tell you, you're flying at the airspeed that is associated with the maximum climb angle, and then I said what you need to do to get to the maximum climb rate airspeed. Accelerate, decelerate. What do you need to do? You're at the max climb angle airspeed. You want to go to the max rate airspeed. Which way is that going to go? Higher or lower?
Lower.
Higher. Max rate is always higher. Remember VX, VY?
VX, VY. It's V out, VY is always a little higher.
It's always higher. Rate is always higher than angle. That's true jet or prop. You remember this chart, and the reason, in fact, we've got, even if I took this junk off of here, you could still do this. Remember, you start at the origin point, and you go to tangent, and what does that give you? That gives you range, airspeeds like max range airspeed, stuff like that. Okay, or the best, in this case, the best rate of climb speed for climbing into a headwind or tailwind. So how do I do that? So this would be zero wind. That's my airspeed. How about for tailwind? Would be somewhere this side of the origin. But if I didn't have this chart that has headwind, tailwind on it, and I said, hey, you've got a headwind you're flying into, could you not just start at the 100 knot point and go there, and come up with a different tangent and determine what your most efficient speed is to do in the climb, 100 knot climb?
What is 100 knot by 300 over 900?
Those are fuel flows. Don't worry about it. So wherever that tangent is, the speed, that's what you read down here. That's all you care about.
But he say tangent, you mean where it's touching?
So if I draw a line straight from the origin and wherever it touches the bottom, now notice, it can sometimes be kind of hard to read. There's kind of a range because, but wherever that thing touches first, that's tangent, right? Straight down, that would be the speed that you would want to give this answer, okay? But if I have a tailwind, that tangent point is going to be further this way on the curve. It's going to be slower. I would use advantage of the tailwind if I can, but it's not the total amount. It's never going to be 100 knots, either faster or slower than the original speed, right? It's going to be a proportion of that. So you could be able to determine, you could derive that. All right, now if I gave you a curve like this, but took the labels off of it, and then gave you, say like just number like A, B, C, D, I could say, you're on the A curve, relate which one is the, and you put the flaps down. Not necessarily which one of those other three would be it, but just where do you expect that curve to move? Does it make sense? So if I go here, if the gear goes down, what do you expect to happen to the curve? It's primarily parasite drag. So this side of that curve is going to be more steep, right? If I do something like, you can see how these curves change with full flaps and gear and full, say it's 60 flaps. I would simplify this and make it a little bit different. So, but nonetheless, you ought to be able to tell what configuration changes do to your curve. So you've got a basic curve, and then what else happens?
I can say the more you put out, like the more severe it gets.
Yeah, well, what's happening here? You've got flaps, and yeah, you're overcoming parasite, but you've also got induced drag, increases too. So yeah, it does get steeper there. So anyway, it's just basic relationships between configuration changes and what that does to your drag and lift stuff. Okay. Let's see. You've seen this stuff a lot before. The main thing, don't get wrapped up too much in there. No, it's a bunch of formulas here. But remember this. When am I doing work?
You're actually responding.
When I'm moving something over a rate of time. So it's actual movement and time involved, right? Or distance. So if I'm not actually moving an object, I'm not actually working, right? So just realize that concept. Remember, these things are available to you anyway. It's going to be on your formula chart. But I'm not, again, this is not for math purposes. This is for, if I give you a situation, is this work, does this not work? Also, is horsepower and thrust exactly the same?
No.
No, it is not. Okay, that's a key point. Thrust, they're not interchangeable. Thrust and horsepower are not interchangeable. Speaking of which, this is what you missed, I think, Andy, part of this anyway. Here, this is jet thrust required, you got power required, horsepower here, and these are for the same airplane, but basically changing the engine and propping. So what we did is we derived this curve to this curve, and notice the change that you have. So if I showed you the curve, you should be able to tell me, even if I don't have this on here, that this is not a jet type curve. It's flat on the side, okay? And so you'd be able to, so if given two similar looking like this, then you should be able to tell me which one's which, okay?
Is there like a reason why, like, it looks like induced drag is a lot higher for jets than it is for... I wasn't here for that.
Oh, that's right, you weren't.
Yeah.
Andy, were you here? Maybe you, okay, both of you guys were listening on that one?
Yeah, that's when I was in California.
Oh, right, okay. All right, let me see, I may need to come up with the other slide here for that. Okay, so basically what you end up doing, and I'm not having you do this, okay, but what we did is we looked at a formula that translates thrust to horsepower, okay, and then we plotted the curve, and that's how we derive this curve from this curve, okay, and so just the shape is different. It's all based on that conversion from thrust to horsepower.
Okay.
So effectively, again, this is the same airplane, just different type of propulsion, and the relationships change. And remember, a lot of that has to do with the fact that effectively a prop, you push in the power, it's there, bang, you've got it. So you don't have this backside of the thrust curve thing. There is a little bit, but it's not near as extreme.
Is that what it does? It really kind of just like compensates for the lag that you have?
Yeah.
with the jet?
Part of that is exactly that. And the fact that in a jet engine, again, from idle to 80%, it's hardly any change at all. 80% on up, then you've got a lot of change. Okay, so the way that the engine responds has a lot to do with that. Okay? But you ought to be able to recognize the difference between the two. Now, here's the thing. Notice this min point here does not coincide with a min point here. It's not the same speed. However, this min point here is not L over D max like it is up here. But notice both curves, L over D max is associated with where induced and parasite drag curves cross. Bing, bing. L over D max is actually up the curve a little bit here. But so that's the key. It's where those two things cross. And that is equal, okay, between the two aircraft. Okay? So that is an important thing to recognize. So what that means is, let me see, do I have that thing? Okay, so remember all the things that are associated with a jet aircraft here. I have that down. We're going to have to dig that one out. I might have to pull up that other set of slides. But recognize that for a prop aircraft, L over D max, or this min drag point, has different associative properties than it does up there. So we had glide speed or glide range and best endurance and all that kind of stuff. Well, it's different for the prop. I thought I had those. Oh, actually, this isn't. So this is kind of weird. So for this airplane, if I start at the origin and I go tangent, I get, that's my best climb rate and all that kind of stuff over here, best range. Or with a prop aircraft, I do the same thing, and lo and behold, that's actually where L over D max is. It's up here. So now, here is your max glide range, and your max endurance speed, and all those kinds of things. So actually a little bit over on the.
So when you go off the tangent line,
So it's different between jet and prop.
I see what you're saying.
Okay.
Essentially, the tangent line is just like a 45-degree line that just like cuts.
Not necessarily 45, it's wherever you start the origin and wherever it hits the bottom of that curve, wherever it touches the curve. So again, if I was like in a headwind situation, I start at this 100 point, tangent line is going to be out over here, and that's going to be my appropriate climb speed. So, that kind of thing.
A little more power if you do that.
Yeah. Now, okay, and then here is the same kind of thing. The thrust available is a straight line across there, but a horsepower, the power curve itself is power available curve is not a constant. So even though it's all at sea level, it's not a constant. And oh, by the way, remember, like this thing, if you ever have to do a formula thing, and I think I've got one in there that I've got, this is, oh yeah, when I got to go over the paper part of the test, we'll figure that out there. But remember, if you're sea level, and if I give you sea level, then this number, you don't need the tables or anything for this, it's just 1. Sea level density ratio is 1. So if you see that sigma in the formula required, just plug in a 1. Pretty easy. Okay, and remember these things here, this is stuff from today. And the fact that those stall characteristics on those different wings are from where they were. So if I said, which ones start at the wing root, which ones start at the wing tip, that kind of thing, you'd be able to pick out from the list which type of wing design those things are. Right? So again, don't just reverse command. What happens? So if I'm at this point and I reduce power, what will be the result? I slow down. I would give you a bunch of. So, for instance, I'm at 130 knots. So I'm here and I've got my power set, giving me 2,750 pounds of thrust. And I pull the power back and I slow down to 120. Where does my power need to go to maintain level flight? It needs to go up here somewhere. So all you have to do is steady state at 120, wherever that happens to be, wherever that hits, come over, there's your thrust required. And also, you ought to be able to recognize the difference between if I took these things away, you'd be able to tell not so much which one has frost and which one has ice, but what happens with a curve if I corrupt the surface with ice or frost. It goes this way. Okay? That's that. Now, let's pull out the paper test, and there's more. Oh, wait, I just want to make sure that I've covered everything. I don't want to leave you guys with any doubt. So that's just some slide stuff that I just pulled off, in the last hour before class. I was thinking, well, I was going to make it a little bit easier on myself. Let me just make sure I've got everything covered here.
Is that the actual test?
It's the test that I'm going to modify.
Hold them down.
Here we go. I knew there was a one math problem yet. It's a multiple guess question. However, it is a math problem too. Okay. Give you an aircraft weight, a wing area, and a coefficient of lift. Let's see. And that coefficient of lift, I associate that with like L over D max, which would be min drag, right? So that's my min drag point. So if I was working on that, and I'm a jet airplane, I want to do max endurance. What speed would I fly? Could I figure that out? Do you think? Let's see how we can do that. This is your formula table. I've added a couple. There's Chapter 6 formula, rate of climb. Oops, see right there. Chapter 9 formula was rate of climb for, what would this one be? This is different. This is actually for propeller aircraft. Notice it's different. It's 33,000 times, something. So if I gave you a propeller thing for rate of climb, you can figure that. And the rate of sink, notice the only difference here is it's basically this in reverse, but what is the drag and thrust? So if you got more drag than thrust, you're going to have a rate of sink. Yeah, but it's basically the same formula as that one there. Right?
TA stands for what? Available and TR.
Thrust available, thrust required, overweight. Yeah, thrust available, thrust required. That gives you possible. Okay, so let's see here. If I did, you define speed, why look, if I use that kind of formula right there, you've seen that formula before. We used it to figure out some other stuff, but we can do it with this too. So if I'm trying to figure out a velocity, I want to find out what my max endurance airspeed or best range airspeed or whatever it is on the curve I want to do. So that's the V. So that's what I'm trying to figure out. So I don't even have to derive anything crazy. But I got to do square root 295. What's the L?
Lift.
Lift. What is that also equivalent to?
Drag.
Lift is equivalent to
Wait.
weight.
Same difference.
Thrust is right.
So those things are the same. So if I gave you a weight of an aircraft, it plugs in. That's how much lift has got to be required, right?
Yes.
So that's on that side of the formula. What's on the bottom? Coefficient of lift times sigma. I knew that was in there somewhere. And what's S?
Area of the wing.
Area of the wing. So I give you surface area of the wing, let's say 500 square feet. Okay, so that goes in here. Right there. Sigma is at sea level, that's 1. And coefficient of lift would be given. I'm not even going to make you look it up on a chart, so I say coefficient of lift is 0.4, whatever. I just don't pull the number out of my rear end. So I put in 0.4 there, times 1, so that doesn't change, times 500 over here, that's the bottom part of the equation, right there. 295 times, let's say, what did I say, heavy airplane? Let's say 15,000 pounds, whatever it's worth. I'm just pulling a number out of my room again. So that becomes 15,000 here. Somebody do some math here for me. 295 times 15,000?
4425,000.
Oh my gosh, 4425,000, okay? Well, I can remember stuff. And then 4.4 times 500? 2,000?
It's like 4 times 500, 2,000.
2,000, but I moved the decimal place.
0.4, yeah.
So it's actually 200, right?
200, yeah.
Makes sense, right? Is that true? Okay, so what's that side of it? So we got square root of 44, whatever, let me see.
22,125.
4.25 million, yeah, 4.4.
Inside the there will be 22,125.
22, what?
125.
125, okay? Then my airspeed, this it may be completely unrealistic. I'll come up with something that's realistic. What's my airspeed? The square root of that is?
148.74.
148 knots. Or 140
So
knots.
you just take that and then you square root whatever the
Ta-da!
math is.
Too tough?
So just
It's
divide
you just
and then-
solve it like simple arithmetic.
Yeah.
It's always the last us.
Yeah.
It's not as difficult as the last test, you're right. But there are, as far as the multiple guess part of it, there's some other things. I mean, you still got to be able to have some stuff together. Oh, shoot, I just turned that on. All right, given the, remember that jet aircraft versus propeller-driven aircraft curve, which derived from one from the other, that slide, you ought to be able to figure out, a best range airspeed with headwind, tailwind. I think I kind of went over that a little bit, that kind of stuff.
Just use the graph, right?
Yeah, and it's tangent line, blah, blah, blah. Yeah, so like that. Okay, and on those, let's see, we talked about thrust and horsepower, they're not interchangeable. So L over D max for power producing aircraft, so different from jet aircraft. For power producing aircraft, L over D max gives you max range and engine out glide ratio, but not max endurance, which it does for the jet. Because that point is not the min drag point. So that's the difference between the two, jet versus propeller. How to be able to figure out a rate of climb based on those rate of climb things that we did. We did one of those problems, right? So we did that already. Stall points, blah, blah, blah. Yep, and what happens on, given, if I give you a curve, tell you where you are on the curve, do something with power or drag devices or whatever, what happens, what's the result? That's it. 25 questions.
I'll do 50.